Consider a square loop of wire in a uniform magnetic field. If we run current through the wire, each segment will feel a force as shown. The front and back forces simply cancel, the top and bottom forces cancel, but they're offset, so they'll tend to twist or torque the loop. Notice also that the tendency here is that the wire is going to expand, right? It's going to intention such as make it larger. And that's interesting, although not for what we're talking about today. This will be actually true for any magnetic dipole, whether from a current or a permanent magnet. A magnetic field will spin it, but not accelerate it linearly, a uniform magnetic field. A compass turns to follow the Earth's field, but it's not attracted to the Earth. This illustrates a little bit more clearly why there's a torque. The forces are offset. There's a force pushing up this way, and there's a force pulling it down this way, but they're pivoting sort of around this point. Calculate the torque and how it impacts motion is topic from AP1, or earlier in APC. So we'll cover the results here, and we hope that you remember them. The total torque is the top torque plus the bottom torque. We can see that they're in the same sense, that this tends to spin it clockwise and this tends to spin it clockwise. And the top torque is half the length away, crossed into the top force times the sine of the angle between them. And it's relatively easy for you to figure out that this angle is still the angle that this line is making to the magnetic field. That will be an important thing later. And the same kind of term for the bottom torque. And so we get that the total torque is the current times the length of the square squared times the field times sine of the angle between them, or the sine of this weird angle. You might recognize that L squared is the area of the loop, so we end up with that the torque is I times the area times the field times sine theta. We now define the magnetic dipole moment, symbolized by mu, because we don't have enough things using mu in physics, as mu is I times A. Also, people often just call this magnetic moment, and they drop the dipole point, because it's redundant except in very esoteric operations. We'll be able to define magnetic moments for things that aren't current loops, and they'll always have units of amp times meter squared. Ultimately, we'll represent loops or magnets or whatever as vectors representing their magnetic moment. Here we see that the magnetic dipole moment is represented as a vector that points in the direction of the dipole's field, where a longer vector would mean a stronger field. And we mean the field as threading through the center of the loop, or through the center of the bar. So again, the torque is the magnetic moment times the magnetic field times the sine of the angle between them. We can see that the twisting force depends on three things: how strong the external field is, how strong the magnet itself is, and how closely they're aligned. The twist is maximal when the two are perpendicular, and there's no twist when the two are aligned. We can kind of see that here. We have a magnetic moment, which we get by doing right-hand rule, right? Put our fingers curling around in the current, and our thumb points in the direction of the moment. And when that is perpendicular to the magnetic field, there'll be a twist that will bring them into alignment. All right, assume loop 1 is held in place. Will loop 2 rotate? We see that they will, because the field due to 1, which are these circular things, and if we take our right hand and we curl it in the fingers, we find that our thumb is pointing downward, so the field is going this way, loops around, right? If it's not on the axis, it loops around to come back in. In so doing, at the point we're talking about, it happens to be pointing up. And the magnetic moment of 2, since we're going around here with our right hand, is pointing this way, so there will be a torque to try and align this arrow with that arrow. There'll be a counterclockwise torque. You can see that a dipole and magnetic field will be in equilibrium when they are aligned, but will also be in equilibrium when they're anti-aligned, since sine of 180 is 0 as well. In that case, the dipole will not rotate, but the equilibrium is unstable. Considering the work done, we could end up showing that there's a potential energy associated with the magnetic orientation of a dipole, which ends up being minus mu dotted into B. So that's kind of nice to know. The torque is the cross product, is mu cross B, and the energy associated is mu dot B. So that's sort of interesting. All right, let's talk about the electric motor. If we attach a loop of wire to an axle, we make something called an armature. The magnetic field as shown creates a torque in the loop spinning the axle. As we notice that we're running a current through that goes, let's see, the current goes this way, out, up here, around, and back. So we get some spin. Normally, the loop would line up with the field and stop, but a device called a commutator flips the direction of the current every time it aligns. That means it's in the unstable equilibrium and will spin to align. Remember, it has some inertia, so even though it's in the unstable place, it will carry past that, and now it's unstable, so it keeps moving down to the new equilibrium, and so on. As long as we keep flipping it like this, the magnet will torque the loop and spin the axle. That converts electric power into mechanical power. Which way will this loop spin? It will spin counterclockwise. The way we have oriented here, if we take our right hand and put our fingers curling in the direction of the current, we would find that our thumb would point to the left, so the magnetic field moment as indicated here is to the left, and it will want to line up to the B field, so it will torque towards in the counterclockwise direction.